Any questions? Okay, so a quick recap. So essentially what we were doing in the last couple of lectures was to motivate and develop a framework for analyzing nonlinear networks. And what did we see? We saw that series is you can use Taylor series as a weapon to analyze nonlinear networks under the constraint that the input is or the swing across the nonlinear device is minimal, right? When I say minimal, that has to be defined, and the definition of that minimal is it has to be smaller than whatever the other nonlinear terms are, right, in the Taylor series expansion. But note that here, when I say it's your input should be small enough, I refer it to the input should be small enough such that the swing across the nonlinear device is within control. It's not as if the swing at the input has to be, has to be smaller than the swing at the terminals of the nonlinear device. What I essentially mean by that is, so let's say I have an input here, and I have a bunch of network here, and I have a nonlinear device here, right? So you have batteries and everything. So let's say this is Vp sine omega naught t. Sometimes I have seen students make mistake that when I let's say the constraint on the nonlinear device is in order to honor your small signal approximation, the swing across it has to be less than 10 millivolt. Let's say after doing the math, this is what we got. That does not mean Vp has to be less than 10 millivolt. It's obvious when I say it aloud, but you have to ensure that you don't make that mistake at the back of your head, right? So Vp can be different values. It can be smaller than 10. It can be multiple times higher than 10, but depends on how the nonlinear device is connected to the rest of the network. Okay, so job of the designer is, let's say I have a requirement that Vp is quite large, let's say 1 volt, but I have to use a device which can only tolerate a voltage swing of 10 millivolt. So job of the designer will be build this network in so that I can handle the 1 volt swing at the input while respecting the fact that the nonlinear device that I'm supposed to use doesn't see more than 10 millivolt of swing. Okay. So this type of configurations you will see later on in the course, but this for the timing, this is something that you should keep in mind. Okay, so we developed the framework for analyzing nonlinear networks under the assumption that we are only interested in the incremental inputs, right? And we saw, 3 related ways of analysis. One was fully mathematical. You write out KCL, KVL, and you write out a bunch of equations and you solve them. One was partially algebraic, partially graphical, right? So you plot the IV characteristics of the nonlinear device, superimpose it on top of the linear characteristics, right? And then see where they meet, where those two curves meet. That becomes my solution. And then on top of that, you can linearize the nonlinear device with its slope, and then find out the output, assuming that the excursions are not large enough. When I say large enough, it's quite evident from the characteristics of the nonlinear device what will large enough be, and it will depend on where you are taking the slope, what type of nonlinearity it is, and so on and so forth. And the third one that we saw was at the end that if I have a network having multiple nonlinear devices, and I wanted to analyze what the incremental voltages and the currents will be, given that this is a quiescent input and this is an incremental input, then we saw that we could linearize this nonlinear network by simply replacing the nonlinear devices with their resistive equivalents, and the resistive equivalents were derived from the slope of the IV characteristics, or 1 over the slope of the IV characteristics around the quiescent point, right? So this would have a quiescent point. Let's say this is V1Q. This is, and this will have a quiescent point V2Q. R1 and R2 are related to the original network from the perspective of the quiescent points. Okay, so now, I mean, we will use this third methodology quite often because it's a circuit design course. So we'll try to deal with circuits, in the framework of circuits as much as possible. Okay, fine. So now, so this stuff that we did till now was for a generic nonlinear network. But now let's get specific. So let's say I have a resistor. So let's say I put elements here in this column. I make a column, and I say on the right hand side I will sketch their incremental equivalence. Right. So if I have a resistor, value R, what will be its incremental equivalent? It will be the same resistor. Why? Yeah. So the slope of the IV characteristics of the resistor is a straight line. 1 over the slope of the straight line is, the slope is G, 1 over G is R. So resistor remains a resistor of the same value. Okay. What about let's say a voltage source, a constant voltage source, not changing with time? Follow the same principle. What should I do? I should first use the IV characteristics of an ideal voltage source. So what is the IV characteristics of an ideal voltage source? Pardon? Line parallel to y-axis. Great. So this is the IV characteristics of ideal voltage source. What is the slope? Infinite, which means 1 over slope is 0, which means its incremental equivalent is a short circuit. Okay. What about a constant current source? What is the IV characteristics of a constant current source? Parallel to the y-axis. Great. Not. What is the slope? So what will be, what should I replace this with? Open circuit, right? 1 over slope is infinity, so it becomes an open circuit. Okay. So let's say I have a specific nonlinear device. I call this is a diode, and I assume that this is a forward bias diode, right? So let's say I have a forward bias diode. So what is the IV characteristics of this? So the equation is, this is ID and this is VD. So the equation of generic equation of this diode will be some constant IS e power VD over VT minus 1, where VT is KT over Q. Right? So when it's forward biased, so what will, or rather, let me sketch this slope plot first, then we'll do this forward bias, reverse bias stuff. So let's say I pick a point where I assume that this is the quiescent point. So let's say VDQ, this is IDQ. So what will be the slope around the quiescent point? Yeah, so slope is del ID VD is IS over VT. And if VD is much greater than VT, which is VT is approximately 26 millivolt. So if VT, I mean, you don't even have to be much greater than, let's say, if VT is 3 or 4 times of VT, right? For example, 100 millivolt or something. Then what can I approximate this characteristic as? Then I can drop that -1. I can assume this to be IS power VD over VT. So then this becomes ID. This hence your dou ID dot VD becomes ID over, right? Which essentially means that if I have a forward bias diode, its incremental equivalent will also be a resistor of value VT upon ID. Note, it's not VD over ID, it's VT thermal voltage over the quiescent drain current that was, quiescent diode current that was flowing through it. Okay. Any questions? So from the specific example of this diode, you can readily see that if I bias the diode with a quiescent current or with a larger quiescent current, the on resistance of the the incremental resistance of the diode reduces, and if I bias it with a smaller quiescent current, the incremental resistance decreases. Right. By the way, this is not the on resistance of a diode. This is the incremental resistance of a diode. Okay. Okay. Any other questions? No. So let's get to something which we haven't yet been dealing with. Let's have a capacitor. So how will we go about analyzing a capacitor? So go back to the original line of thinking, that what did we do when we have a nonlinear element? We tried to find out the IV characteristics, we perturbed it, and we basically dropped the higher order terms, right? So that was the way of going ahead with it. So let's do the same thing here. So when you have a capacitor, what is the, I mean, we'll just put the capacitor, bias it with a certain voltage. Let's say VCQ. So this is VCQ. Okay. And I have a incremental voltage delta V. Okay. So what is the IV characteristics of a, I mean, what is the governing condition for I and V in a capacitor? Yeah, right. So I is equal to C dV dt. Great. So let's say when I have a constant voltage, right? Let's say del V is 0. When I have a constant voltage, what is I? I is 0, right? Great. So let's assume that we will not assume I to be 0. We'll assume I to be some I, and then proceed with it, and then see what happens. Okay. So let's see. So let's assume that we have perturbed the capacitor with a voltage delta V, the voltage across the capacitor with a voltage delta V. So what should I get? So let's say I get a new current which is I plus del I, which will be equal to. Oh, by the way, one quick comment before I proceed. So moment we say that I equal to C dV dt, we have made an assumption. Pardon? I can't hear you. Can you repeat? There is no initial. Yeah, okay. Not really, right? So this is not the fundamental relation between capacitance and IV of a capacitance. This is a fundamental relation of an IV of a linear capacitance. Pardon? Okay, step change in the voltage. Even if you have a step change in the voltage, this still holds, right? You want dV dt probably will be infinite in that case. Right. We assume the capacitance is constant. The relationship actually is I is equal to C dQ dt, right? Under the assumption that capacitance is not changing, then you bring the C term out, right? Okay, so let's stick with this for the time being. So this essentially is dt of CV. So when I change the voltage by delta V, what happens? Oh, by the way, even if was there a question? Even before I proceed, so let's say, sorry for going back and forth. So let's assume that this resistor here, obviously this is a linear resistor. That's why the IV characteristics was a straight line, right? So had the IV characteristics not been a straight line, then I would have had to replace this nonlinear resistor with a linearized equivalent, whose value would have been 1 over slope of that IV characteristics, right? So what I mean by that, if in case I had a nonlinear resistor, right? So R and L, let's say, the IV characteristics would have been something like this, maybe. So in that case, I would have had to replace this nonlinear resistor with its incremental equivalent, which is equal to 1 over slope, right? Which is again 1 over slope, and depends upon wherever you are taking the slope. So this we already know, but at its core, what does a nonlinear? Another definition of nonlinear resistor can be that the value of the resistance is dependent on the voltage across it, right? If the value of the resistance is dependent on the voltage across it, then I can say that the IV characteristics is nonlinear, right? So if the value of the component changes when we apply different voltages across it, then the IV characteristics of the component will be nonlinear. Is that clear? Is that evident, or it's a bit murky? I want a response. Pardon? Oh, should I repeat? Okay. So when I say I have a resistor and I equal to, or let's be going to V into I. So say V is equal to R times I, right? I am assuming that in a case of a linear resistor, R is constant. So when I say it's a nonlinear resistor, what am I assuming? R is not constant, right? If R is constant, then this automatically means it's a linear resistor, correct? So, since we are doing IV characteristics all the time, let me write in this form, I equal to, let's say, G times V, or V by R. So the relationship between I and V is linear only when R is constant. Let's say R is a function of V. Then obviously the relationship between I and V is not linear, right? So another way of stating a nonlinearity in electrical domain is the fact that the component value changes when you apply currents through it or voltages across it, right? So if the component value changes, then naturally the component value can change maybe linearly. That can happen, but that change in component value makes the IV characteristics nonlinear, right? Is that clear, or should I spend more time on this? Okay. So the reason I was harping on this is, similarly, if a capacitor is supposed to be nonlinear, what would it mean? The value of the capacitance will vary with the voltages applied across it, right? So in that case, if I apply delta V, so naturally the capacitor will change from C to C plus delta C, and the voltage naturally changes from V to V plus delta, right? So if I break it down, this becomes so again the same volt. So this term and this term go because they are the same. Now can you comment on the magnitude of this term with respect to the other two? Yeah, so this is the higher order term, like two increments multiplied to each other. So in a small signal approximation, I can neglect that, assuming that negligible stuff is smaller than the other terms that are available. So your del I becomes ddt and now if we assume that the capacitance is linear, right? This is a generic format. Now if we assume that the capacitance is linear, how will this equation get modified for a linear capacitor? What I mean is the capacitor is a linear element, not the capacitance change is linear. So if the capacitor is a linear element, how will I modify this? Del C will be equal to 0, right? So for a linear element, so del I will be del V times. Or I can take the C out, C. Right? So what is the, so this was my initial state. Now, if I want to replace this this quiescent state with its incremental equivalent, which means I drop the voltage source. Let's say this is del V. What will this element be now? The stuff inside the box will be. Should I replace it with? Pardon? So what am I looking for? I am looking for the relationship between del I and del V now, right? I'm looking for the relationship between del I and del V. In the incremental model of any device or any network, all I'm interested is the relationship between the increments of current and increments of voltages, right? So the increment is the signal, right? So what is the voltage signal? The voltage signal is del V. What is the current signal? It's del I. So what is the relationship between del I and del V? C D del V dt, right? So what type of relationship this is? This is that of a capacitor, right? So a capacitor remains a capacitor. A linear capacitor remains a linear capacitor, just like a resistor. But let's say, had this been a nonlinear capacitor, right, where the capacitor would have been changing, right? So what should I have done? I can't hear. Can you repeat? I still don't understand. Right, exactly. Del C will not be equal to 0. Correct. So del C will not be equal to 0, which means I cannot replace the capacitor with its, I cannot just simply say that the original capacitor remains a capacitor. So I cannot do this. So, but note that this is equal to what? This stuff is essentially del Q. Correct? This is del Q. So this is d dt of del Q. In case of a capacitor, the mother equation is I is equal to dq dt. Right? So in case of a nonlinear capacitor, then what should you replace a nonlinear capacitor with? There will be something inside the box. What will be the stuff inside the box? Okay, so let me give another hint. Come again? Capacitor with capacitance at that particular point. Okay, so it's basically you are saying that when you say capacitance at that particular question point, what do you mean now? Analysis, we get a particular DC operator. Right. Yes, you're right. Okay, not really. It's not so. So again, we have to go back to the fundamental IV characteristics in case of a capacitor, right? So I is equal to okay. So what is in case of a capacitor, C is equal to Q by V, right? So if C is equal to Q by V, this is the fundamental relationship of a capacitor, right? So I equal to C dV dt comes because we differentiate Q, right? So everything comes from here. So in case of a nonlinear capacitor, we have to go back to this original relationship. Okay. So now if that is the case, and I say that I am not interested because things are becoming murky in the current domain, I will go back one step and I will analyze everything in voltage domain, in charge domain, right? If I do that, then what is the, can you take an educated guess? You don't even have to take a guess. You can just, what will be the incremental analysis in case of a charge domain? So let's say this is quiescent charge, C V quiescent. So I change voltage. So what will be the equivalence of a capacitance? No, why the distance? So I change, so let's say I change voltage from VQ to VQ plus delta V. So the capacitance changes to C plus delta C. This becomes VQ plus delta V. So the charge will also change from, right? So again, I do the same thing that we have been doing. So this becomes CVQ. Right? And I neglect the other term. So this cancels, right? So so now what is the relationship between when we are talking about the relationship between note that we are, so hold on, so this probably will not lead to the argument. Okay. So your del Q, your capacitance will now be, ultimately when you are talking about a nonlinear capacitor, we are interested in the increments of charge when I have a unit increment on voltage, right? So ultimately we are interested in del Q del V, right? So in this case, your del Q del V will be del C V. Correct? So whatever this is, you will have to replace your nonlinear capacitance with, right? So you normally don't see these type of expressions because again, it doesn't give you too much intuition. So what we did, most simulators or even the literature tends to do is to limit our capacitance, incremental capacitance to this expression of del Q del V, right? So in other words, if I have a QV characteristics in case of a capacitor, let's say I have a QV characteristics of a capacitor. In case of a linear capacitor, the QV characteristics would have been a straight line. In case of a nonlinear capacitor, it can be something. It can be something, some nonlinearity. In order to extract the value of this incremental capacitance, what do I need to do? I need to take the slope at whatever quiescent point I had. Okay, I need to take the slope of whatever quiescent point I had, and take, if this slope is del Q del V, that will be my equivalent incremental capacitance in the incremental picture. Okay, now does that make sense? Okay, so now what is the conclusion? The conclusion is if you have a nonlinear capacitance, or in general, if you have a capacitance, you can replace it with another capacitance of value del Q del V. In case of a linear capacitance, this is general. In case of a linear capacitor, this will remain C. Okay. Similarly, if you have an inductor, in case of an inductor of value L, again, if it's a inductor of value L, and let's say it's a linear inductor. When I say linear inductor, again, the value of the inductance is not changing when the current is flowing through it, or voltage is sinusoidal voltage, or any voltage is developed across it. So in that case, this will remain an inductor. Okay. Any questions? Okay. So till now we have been dealing with. We started off. If I have, 1 minute recap. We started off with a requirement of an amplifier, or an amplifier that can amplify power. We saw that cannot do it with an LTI system. We need nonlinearity. The moment we require nonlinearity, we need a framework to analyze nonlinearity. The framework for analyzing is incremental, small signal. So we did that. We got around that framework. We found out what are the ways of generalizing any type of nonlinearity in a network, right? So now it's time to get back to business again, and let's go back to our 2-port network in order to get our requirement of a power gain, right? Questions? You had a question? So let's say I have a 2-port network characterized with generic I and V, where the input port current is some function F1 of the port voltages V1 and V2. The output port currents are some different function of V1 and V2, right? And we seek to find out what is the relevant model of this generic nonlinear network that is helpful for our analysis purposes, right? Just like we did for one single element or one single loop. So in this case, let's assume that I have two ports. So what is the way of analyzing this and going about this? Okay, so now we are all experts in analyzing Taylor series for a single variable function. Now this is the multivariable function. Nothing changes, just that I have to do partial derivatives with respect to whatever is the dependent variable. So in this case, I1 is F1, V1, V2, right? So let's say this is I1Q, V1Q, V2Q. Q refers to the quiescent point that has been set up somehow. We have a battery somewhere inside, outside, but it has been set up somehow. But this is what it is. So now we further assume that we have some voltage excitation somewhere in the network, that voltage excitation or some excitation in the network, and that excitation created a change in voltages across the two ports. Mind you, again, I am considering a two-port. It need not be two-port. It can be an N-port network, right? So just that the analysis will extend to multiple ports. Take two-port as a vehicle to analyze them. So let's assume we have applied. We have applied incremental voltage somewhere, because of which the port voltage is increased from V1Q to V1Q plus delta V1, and V2Q from V2Q to V2Q plus delta V2. So the incremental current or the increment in the current I can express as delta I1. Similarly, for the other port, this will be okay. So now what do I do? What will be the next step? Taylor series of, you can take either one of these two and expand, and then we'll do the other one. So if I expand this one, what do I get? What is the independent variable? Voltage. Voltage is the port voltages are independent variables. Good. So now I expand it in a Taylor series. What is the first term in the Taylor series? The quiescent position, the position from which I am starting the analysis, right? I already know where I am at, right? By doing some numerical analysis or something, I'm interested to see with the extra increments, where am I going, right? So the original first term is always the quiescent, and this is a known term. By known, I mean you have to put in some fight and analyze nonlinear equations and all, but this is known. Then the second term is, now things get interesting because I have two variables, right? So what should I do when I have two variables? I'll assume that one variable is constant, the other changes its effect, and then I should assume the other one. So let's do that in this case. So this will become del V1, del V1. Obviously, I'm assuming moment I say del, I assume that V2 is not changing, but this has been evaluated at a certain quiescent point, right? This partial derivative has been taken at a certain quiescent point, and that is obviously V1Q, V2Q, right? So similarly, you will have V2 del F1, del V1, again evaluated at certain quiescent point, and you will have higher order terms. Okay. So now again, small signal approximation means I have to limit the excitation such that the higher order terms are negligible, which means that conveniently I can neglect them, which means these two cancel out, I mean, this anyways cancel out, but the key thing is I get a linear relationship between the incremental voltages and the incremental current. This will be 2, right? Okay. Similarly, I mean, since it's whatever happens in port 1 as far as algebra is concerned, happens in port 2 also. So I don't have to write the entire stuff again. I will simply copy. So delta I2 again will become del V1, but now the function is different for the port 2. So this becomes del F2 del V1, but evaluated again at quiescent points V1Q, V2Q. Okay. Okay, any questions? Okay. So as it turns out, these are so commonly used that we refrain from expressing these terms in terms of their partial derivatives all the time. We just replace them with a smaller notation, and the notation is what is the unit of these terms? This, I mean, all of these partials. Conductance, right? Its unit is 1 over I by V, it's conductance. So generally you have these matrices, right? Y matrix, Z matrix, H matrix, and so on, right? Multiple of them. Which one do you think is suitable? Y parameters, right? Y matrix. So we basically replace them with their Y parameter equivalent, and we say this is del I1 is del V1, and this is Y11 plus times del V1 plus Y21 times, sorry, Y12 times del V2. Similarly, delta I2 becomes Y21 times del V1 plus Y22 times del V2. Again, what are the significance? What is the significance of these notations? Why do I say something like let's say Y12? What does this 12 mean? Yeah, but I mean, what if I just tell you that YMN? What will that MN mean? What will the subscript? What will the subscripts M and N mean? Or in this case, what does the subscripts 1 and 2 mean? Can you speak louder? I can't hear. Right. Effect of, in this case, the effect of port 2 on port 1, right? So dependent variable is port 2, independent variable is port 1, hence Y12, right? So the cause is to the right and the effect is on the left, right? So this is the cause. This is the effect. Okay. So again, this dels and dels people use all the time in a small signal. So again, we thought that why should we use del all the time? It's better to come up with nomenclatures. So the nomenclatures that we tend to use is the following. In case of, let's say, I have so this is now nomenclature. The nomenclature is as follows. So let's say I am talking about quiescent operating points, quiescent currents or voltages. So we say that if I have a voltage across two terminals A and B, I will denote them as capital V subscript capital AB. So this is quiescent. Okay. If I have to denote incremental, that is delta VAB, right? So this is referred to as small v subscript small ab, right? So this is incremental. Okay. So there is one more that is often you'll be seeing we are interested in both the incremental and the quiescent. That is, I want to see the total signal at a particular node, right? So if I have to find out the total signal at a particular node, what do I need to do? I'm not talking about nomenclature now. Let's say I know the voltage across a diode is let's say is 1 volt, and the voltage across it is swinging by, I mean, when I am applying a sinusoid, the amplitude of the sinusoid across the diode becomes, let's say, 10 millivolts sin omega t. Then what should I do in order to find out the total voltage? Pardon? A summation, right? I basically add up the quiescent and the incremental, right? So then I get the total. So the total is total voltage is essentially VAB, the quiescent VAB plus the incremental VAB, which is referred to as small v capital AB, right? So this is total. So these are, I mean, when in doubt, write it out fully and make it explicit that you are talking about total or incremental or apply delta. All are okay with me. But when you are using this when you're using the notations, ensure that you are right. Otherwise, it becomes difficult to understand what's on the paper and what's on your mind. Right? Okay. So having said that, since we were discussing only incremental pictures till now, so what we will do, so again, I mean, obvious thing here is when you are using letters, they have small and large, but when you have numbers, you only have one set. So we'll assume that when we are using small v, small I, then it's incremental. So in this case, del I del I1 will be small I1 is y11 small v1 plus y12 small v2. Similarly, I2 will be y21 v1 plus y22 v2. And this again quite popularly, I mean, once you write it in this format, it becomes quite obvious. This is a matrix format. So very popularly this is used for problem solving because system of linear equations are most conveniently solved using matrices. Okay. So now that we have arrived at this juncture, which means that we have now a framework of the same old nonlinear network, whose incremental equivalence or whose incremental relationship between the port voltages and the currents can be represented by a system of linear equations, and the governing parameters for the system of linear equations are the incremental y parameter matrices. By the way, this is important, so I should write it down. So this is incremental y parameter matrix. This incremental term is important because you should, even though it's not explicit here, simply because it's a nonlinear network, these values of y11, y12, y21, and y22 are bound to change when I change the quiescent points. Okay. Okay, great. So now, now that we have essentially fully linearized the system, right? So now there is nothing nonlinear, right? So nothing nonlinear. So, and also, do you think in this network, do we have any constant voltage or current sources inside this incremental network? No, right? Why? Because we saw that a constant voltage source will be replaced with a short circuit. A constant current source will be replaced with an open circuit. There are no constant voltage and current sources. There are only incremental linear networks. Okay, great. So by the way, when we represent again, so this when we represent this mathematically, what is the can I express this in some form of circuits? Ultimately, these are all currents and voltage, right? I should be able to. So let's take I1 for example, right? Let's take I1 for example and concentrate on this equation. What is this telling us? This is telling us that there is certain relationship between I1 and the ports 1 and 2, right? So this is port 1 and this is port 2. So what is the relationship? First relationship is the first term, that is the current that is flowing in. Obviously, the current that is flowing in one terminal is also flowing out of the other. Sorry, this is I1. Otherwise, nothing will make sense. So the current that is flowing in through the top terminal or into this port is dependent on the port voltage V1, right? It's dependent on the port voltage via proportionality, right? And if we assume again, all these are positive real numbers, right? Y1, all the y parameters are positive real. Then what can you comment on the type of element that Y11 represents? It's a conductance, right? It's a conductance of value Y11, right? So essentially this is a conductance of value Y11 or resistance of value 1 over Y11. So this takes care of the first term. What about the second term? So what does that represent? This tells us that the port current of the current in port 1 is dependent on the voltage across port 2, right? So, and the dependence is again that of a constant, right? Some constant Y12 times V2. So what type of element is this? It's a transconductance. It's a voltage dependent current source. The current that I am drawing through port 1 is dependent on the voltage of somewhere else, right? If the current is only dependent on the voltage of that port, it's a resistor or it's a resistor or a conductance. Or if it's dependent on a voltage of some other port, it's a transconductance, right? So in this case, this will be a transconductance of value Y12 V2. Direction of the current, or rather I have to close the loop. What will be the direction of the current? Pointing down or pointing up? Pointing down clearly, because ultimately this current has to be Y11 times V1 plus Y12 times V2. Okay. So now let's move our focus to the output port. So similarly, what is the easiest one to deal with in the output port? Is Y22 V2. Again, it should be a conductance of value Y22 or resistance of value 1 over Y22. And just like in case of port 1, this will be a transconductance of value Y21 times V1. So that the total current that I am drawing into port 2 is Y21 V1 plus Y22 V2. Okay. So before we move forward, let's say I ask you, I give you a nonlinear, generic nonlinear network. And this is I F1 V1 V2, F2 V1 V2. And let's say you have this nonlinear network, and I ask you to experimentally extract the values of the Y parameters, incremental Y parameters, right? Not mathematically, not writing equations. You are in the lab, you have a nonlinear two-port. I want you to experimentally find out the incremental Y parameter matrices. That is increment, you have to find out Y11, Y12, Y21, Y22 individually. So what will you do? What is the, talk me through the process. You have voltage sources, current sources, this network sitting in the, it's biased properly, biasing is given. So now talk me through the algorithm. How will you go about extracting it? So let's take Y11 to start, incremental Y11. What will be the algorithm? Port 2 should be short circuited not in the incremental sense, in the total sense. See, when you are handling a network, it doesn't know what you are interested in, right? You might be doing incremental analysis for your sake, but for the network is all currents and voltages. Okay, so when we say I am interested in incremental Y11, what am I saying in terms of the total voltage or total current? It's constant at which port? I can't hear. V2 is constant, right? So what is your test setup then? So let's say we want Y11 experimentally. So in plain English, what is Y11 again? So from this, in plain English, Y11 is the relationship between I1, incremental I1 and incremental V1 when V2 is, incremental V2 is not constant, it's 0. Right? So, I mean, from maths, it directly comes out, right? So I1, so if V2 is equal to 0, I1 is Y11 V1, which means Y11 by definition is I1 by V1 when V2 is equal to 0. Right? So now you are entrusted with the job of extracting the value of Y11 experimentally from a device or a network that has been given to you. You don't have to bother about quiescence, it has been set up. Somebody has set it up. So which means that you have this network with a battery and everything inside, battery, current sources, whatever is necessary, everything is inside. It's a nonlinear network. I need to extract Y11. What should I do? You have access to port voltages and port currents. I mean, these two ports are accessible to you, right? So now tell me the algorithm. Okay, so you say bias. If I say I short it, if I say I short the port 2, what's going to happen? Correct, right? So the thing that you have to check is before applying anything, what is the quiescent voltages and the currents flowing in and out of the port? Correct? Do you agree? So in the setup that I have shown, obviously quiescent current will be 0 because it's open circuited on both sides. but the quiescent voltage need not be 0. Right? So you can have a quiescent voltage V1Q. You can have a quiescent voltage V2Q at the port 2. Correct? So now if I, because I told you that I11 is equal, Y11 is I1 by V1 when V2 equal to 0, I go ahead and short this port 2 voltage. Will am I disturbing something? What am I disturbing? Can't hear. I am disturbing the quiescent voltage at the port 2. Right? Moment I disturb the quiescent voltage, all my incremental parameters are junk. Right? Incremental parameters again are strong functions of quiescent operating points. Okay. So you cannot simply short it because it looks like from the maths V2 equal to 0. Right? So V2 shorting is only one particular case of V2 equal to incremental V2 equal to 0. So other thing, so if I cannot short it, but I want incremental V2 to be equal to 0, then what should I do? Capacitor will come later. You have access to voltage source, current source, indefinite of them. What will you do? I'll put a voltage source. I'll have to hold this voltage so that it doesn't change. How do I hold a voltage? I put a voltage source of value V2Q. Okay. So that is beginning, one step. What is the next step? I need Y11. Correct, right? So I need to have a source here which gives me V1Q plus some delta V1. Right? Okay. So firstly, the first thing is to set it up. I'll have to set it up with a battery of V1Q. And then I have to apply an increment, right? How do I apply an increment? I have to, if I have V1Q, let's say 1 volt, and I want to add a small sinusoidal excitation, what should I do? I have, let's say, another voltage source. How do I add an increment? In series, right? So I add an increment delta V1. And then what do I need to check? This I1. So this I1 will be what? Right. So this I1 will be I1Q plus delta I. So I missed an intermediate step, right? The intermediate step would have been by applying V1Q, I should have checked I1Q first. Then when I apply delta V1, I'll know the change. And now that I know delta V1, because I've applied it, I know delta V1, the relationship between delta I1 and delta V1 will be my Y1. Right? So this is like multi-step process, right? Just because from maths you see that you short this, you get that, doesn't mean that that's how your networks will work. You have to respect the fact that the network has its own requirement of quiescent conditions, right? Unless you set it up properly in a proper quiescent condition, nothing is going to work. Okay. So similarly, walk me through. So let me complete this thought. So this becomes, so Y11 then becomes delta I1, right? Delta V1. Similarly, let's say I want Y21. Let's say, so Y21. Again, it's the same network. How will you set it up? We want Y21. So Y21 is what? No, I have to first set it up, right? So my question is, will the original network, will this network be okay to find out Y21, or do I need to change anything? Pardon? So what is the definition of Y21? I2 over V1 when incremental V2 equal to 0. So do you think this original network is fine, or do I need to change anything? Original network is fine, right? But what should I observe now? I should be observing, obviously, the first thing I needed to observe was I2Q, right? If we had I2Q in the absence of del V1, then only I can find out what the increment will be. And then from this original network, I will be able to, from the same network, I will be able to find it should be equal to delta I2 by del V1. Okay. Similarly, walk me through the process of what's going to happen if I want to find out what is Y22. I mean, now this should be pretty straightforward. So I want Y22. What is Y22 by definition? Is I2 over V2 when incremental V1 is 0. So what is the algorithm? How do I set it up? Right. So the port 1 voltage will be constant because for incremental V1 is 0. When I say constant, it has to be constant with the value of the quiescent voltages, right? You cannot just put any constant, like 0 is also a constant, right? You just short it, it becomes a 0, but in that case, the quiescent voltage will also change, right? So you cannot, so your V1Q becomes this, then what? This is port 1, this is port 2. So what will you do with port 2? Right, so I apply first V2Q, find out what I2Q will be. This is one reading, then you apply delta V, and then you find out what this incremental current will be. So your Y22 will be del I2 del V2. And from the same setup, you should be able to find out what your what Y12 also is. Okay. Make sense? Okay. So before we leave today, so why are we doing all these things? So all these things we are doing because we know that we have an incremental voltage source with some internal resistance, let's say RS, which has been connected. I need to connect it across one port, and probably there is a resistance associated with the other port, and I want an amplification between V0 over Vi, and hopefully that will be equivalent to a power amplification, right? So we'll see whether or not this is equivalent to that or not. So what do I now need to do? I know that the stuff inside the box in an incremental sense is this. What is the most obvious thing that I need to do? I need to now figure out whatever is V0 over Vi. Right? So we need to figure out what is incremental V0 over Vi. Once we do the algebra, we need to then see, is there certain properties of this two-port network, or are there certain properties of this incremental Y parameter matrix that will give us amplification? Okay. So that is something that we'll do in the next class. What I request you to do is do this algebra yourself, right? I'll start off from whatever V0 over Vi you tell me you found. Okay. Okay. You can stop here.